Good afternoon and welcome to Webinar Wednesday. Today we are joined by James Freeman, Multi-Vendor Modality Manager, CT Nuclear at Phillips Healthcare. Webinar Wednesday, we'd like to thank our sponsor, AllParts Medical. AllParts Medical provides multi-modality, multi-OEM replacement parts from its 158,000 square foot facilities in Nashville, Tennessee. In addition to parts sales, AllParts also provides customers an extensive array of in-depth training classes and technical support before and after the sale. An ISO certified quality management system helps deliver an industry-leading warranty rate. So for more information, please visit allpartsmedical.com. And just a quick reminder about saving the date for our fall MD Expo. We're headed to the Mohegan Sun Casino and Resort in Connecticut from October the 8th to the 10th. Please join us for 3 days of education, networking, and the latest advances in medical technology products and services. For more details and registration details, please visit mdexposhow.com. Today's webinar, as usual, is eligible for 1 CE credit from the ACI, and you can obtain your CE certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Okay, let's kick off today's webinar by giving away one of our Webinar Wednesday 10th anniversary prizes. Today's prize is a pair of Apple AirPods. So using the questions feature on your dashboard, let me know the answer to the following trivia question. June is National Adopt a Cat Month. So what is the name of the cat portrayed as a lazy, fat and cynical orange tabby cat who originally appeared in a comic strip and has his own movie? I'll reveal the answer and our winner at the end of the webinar. We'll be wrapping up today's presentation with a live Q&A, so please submit your questions anytime using the questions feature on the webinar dashboard. As I mentioned earlier, our presenter today is James Freeman, and he'll be discussing an introduction to computed tomography. James, you may begin whenever you're ready.
All right, thank you very much, and hope everyone has a good day going on. And as stated, this is introduction to CT, not how to repair CT, or some of those that may be already working on CT. This may be just a rehash, but wanted to make sure that we covered all the base material, realizing that a lot of us still understand this technology, but there's quite a few people out there who have not seen it yet, so we'd like to be able to share that with them today. I'd like to cover a little bit of my background in CT, some of the things that we definitely see in computerized tomography, the functionality, what it's used for, how we deal with different elements with regards to the design, and what we see as a standard type of CT environment. Also, cost to serve. I'm involved with the operations side of the business, where we look at service and what side systems we service and which ones we consider direct service, and then how CT tubes are enabling to doing that, and then the all parts operation as an element to provide whatever you need. So I started in the Air Force working radar and F4 Phantoms in the 70s, so late 70s that is. So worked electronics, was overseas in Europe during some of that time as well. And really the military gave me the electronics knowledge I needed to be able to move forward in my career. So I started with medical imaging in 1982 with GE. I started with X-ray products and then moved into CT around 1983. So been doing this a few years and seen a lot of changes in just what's happened in not only computers, but in CT design. The philosophy of slip rings was introduced, multi-slice CT, different types of computer in engagement with regards to how fast a computer has changed. Originally, the first CT that I worked on was an 8800 CT, had 96K of RAM and ran at 6 megahertz. Okay, so that's the early days of CT. So in a few occasions, I actually was the installer of a hospital's first CT. And during that time period, hospital needed a certificate of need to prove that they actually could afford and use a CT for patient studies. So I went to work in the mid 80s for a company called Medic that actually had a mobile CT fleet and followed those mobile CTs around for a while. Then eventually hospitals gained traction to have CTs almost at all facilities now. So not only have I been scanned on the scanners that I've repaired, so has my family members as well. And so the technology has really impacted a lot of people's lives that I know of, and especially mine, that I've been able to stay in this industry and learn more every year. So my goal is to always learn something new every day. So we're CT scanners used for, right? Hospitals, clinics, emergency urgent care. That is one of the primary things that a CT scanner gives hospitals, is the ability to have a trauma center rating. If the CT scanner is down, quite often they can have to divert patients to other hospitals that have a CT scanner that is operational. So with regards to that, there's a lot of pressure on keeping those units up and running if they only have one at a given facility. Obviously, if they have multiples, they can defer to other CT scanners, but it still becomes your critical care item. Neurology, angiography, abdominal, pelvic, radiation therapy planning, and then in conjunction with more advanced version of radiation therapy planning, you have PET CT, which then we get into positron emission tomography as well. So one of the things that CT first brought to the table that didn't exist beforehand was the ability to image brain tissue. At conventional X-ray, you could shoot through the skull, but you can't see the individual brain structure or anything. It's all superimposed on a 2D plane. So it brought in 3D as well. So the first CT scanners were produced by EMI, and they were head-only scanners. Then later on, as scanners got more efficient, aka larger X-ray tubes, larger detector arrays, then the whole body was scanned, after that initial first release of CT. And EMI was in the mid to late 70s, and then CT really took off in the marketplace in the United States in the early 80s. So one of the things that we are with a CT scanner, we're very concise with, and that is there's a scaling system. It's called the Hounsfield scaling system, but we know it nowadays as CT numbers because obviously the computerized tomography. Essentially, they're the same. Water, distilled ionized water, should have a CT number of 0 plus or minus scientific error, which will be about 4%. And then bone will have a high positive CT number, and then air will have a negative CT number, almost the full range. So this is called Hounsfield scaling, or CT numbers as we know them today. So one of the things that we hear a lot about in the industry, obviously, is that CT has a higher dose. But along with that higher dose comes the ability to see things in a greater detail. So with a conventional X-ray room, you may take a AP shot and a lateral shot. Those are two shots. They might even be 1 millisecond each in time. So you're going to have a very low dose. But out of that, you only have two 2D images to work from. And, you can see fractures. You can see a number of elements from them. But with CT, as we rotate around the patient, at least a minimum of 180 degrees, but in most cases 360 degrees, we have a lot more of those views. So that means that we're going to have a lot more detail about with the structure of the body and the anatomy of that body. So that's one of the reasons why it is a little bit higher dose. There are techniques to minimize the dose, but at the same instance, that's what happens. So let's see, my slide deck has kind of gotten on its own there. There we go. All right. Sorry about that. So neurology is the first thing. Think of a trauma event where there's a car accident, the person hits their head. So one of the first things with a CT scanner, why it's rated as part of the trauma center rating, that person comes in with a head energy. They don't know whether it's a bone fracture with the skull or a hematoma or a couple other things. The patient may not be very responsive. So with that, we can scan the person's head. We can then apply to a couple of different data set algorithms. So that we would call raw data when we first scan the person, and then we can reconstruct that data with different frequency response filters to be able to enhance bone or soft tissue. In this case, you could see the upper images with regards to a patient. You can even see the optic, in some cases, the optic nerve path, inner air canals, a lot of detail. The bottom images, you can see a little bit of extra information because of the contrast within the veins of that person's brain. So you can see if there's a shift in the hemispheres, all kinds of information with regards to trauma, with regards to what that patient may see. So what that means is we could scan the patient one time without contrast and then generate an image set for both bone and soft tissue. Then we can scan them again with contrast and then do the same thing with bone and soft tissue algorithms again to enhance the data set without having to take the patient off the table multiple times. So with regards to lungs, what we can see is a lot of detail. We can also change the window level settings with regards to enhance the data set. So you see basically the two bottom images here more like a AP lateral type shot. We can then reconstruct the data in multiple planes. Typically, the top images that you see are more axial-based image reconstruction, but we can also do them across plane as well from that data set that we scanned with. So we can use that data set to produce a lot of different images. Typically, like you said, like we normally see, is the ones that are produced to mimic more of an axial type cut through the body. Cardiac CT, obviously, the heart could be beating, you're breathing. So what we could do is we can actually speed up the gantry rotation and then trigger off certain waveforms that the heart gives to know which valve may be open or chamber may be full or closed, and just collect data just for a snapshot. And then as we rotate around the patient enough to have at least 180 degrees worth of data, we can produce an image with maybe the chamber full or the chamber empty or valve open or closed. The image on the right would be what we call a false color image, where we take the data set and each CT number has a unique material like calcium or whatever we get back, and we can false color that CT number to generate an image that you would see on the left. So a lot of things we could do in CT have to deal with how well we calibrate the machine as well. So you see a normal CT right here with abnormal diseases. We can tell liver, we can see fatty liver. We can also determine what's going on with different parts of the body. You can, in the case of iodine, if the patient drinks or is injected with iodine, we can see the iodine flow through the veins as well. So we can look at a number of details within the body. And understanding how we use this data or produce this data. We're looking at grayscale here because the system is scaled that way, right? We don't typically see images in a color format. They're just drawn out here to understand what anatomy we're looking at. So also it's been used for lumbar spines in conjunction with doing MRI as well. So with regards to the lower back, inner disc spaces, a lot of times CT, when it was first released, MR was not in the market at the time. So you would see a lot more studies with regards to backs being done with CT. Currently, more studies are done on the MR side because of we get artifacts from bone, our sharp edges in bone, especially. So when MRI was first released, it kind of took over the soft tissue side of this aspect. So let's see here. The next image is we see, basically this is what majority of CT scanners are based on this topology now. This is what's known as a third generation CT topology. The reason I say topology is first, second, third, and fourth and fifth generation CTs all were aligned hardware-wise a little bit differently to acquire an image. But when we get into multi-row, multi-slice scanners, all of them are basically third generation design, where the tube and the detector will rotate around the patient. And basically the center of that spot in the gantry we call ISO center. So we'll rotate around ISO center and gather data as we rotate around. And again, as I said, CT, we require a minimum of 180 degrees rotation to produce an image. But originally we did 360. The more data, the less noise in the image is the best way to put that. And so that's one of the reasons why you'd want to do it. So the X-ray beam obviously is ionizing radiation, so we like to minimize as much as possible, but it's constrained into a slice of a thickness, maybe a millimeter, 5 millimeters, 10 millimeters of what we're interested in acquiring the data for. So we have the detector array, which is typically a crystal-based detector now. And radiation and crystals are not really friends, so to speak. So over time, radiation will degrade the crystal structure and the modules have to be replaced. And then we have the data acquisition subsystem behind it. And then with regards to that, let's see, I'll back up one slide back here. It's slide deck's moving on me. So what you see on your right-hand side would be like a single slice rotation. It's spread out a little bit so you can see as it rotates around the patient. Typically with a pitch of 1, the green lines would be up against each other and filling in a helical fashion. So we think of this as a volumetric data set that we're actually collecting of the data of the patient. On the slide on the far right, the multicolored slide, that's a 4-row detection. Then we get into 16, 64. So if you think about it, we're rotating around the patient. Now, if we move the table at the same time, we're creating a volumetric data set. And then out of that data set, then we can project images out of that collected data set and process them. So that's what multi-row gives us, is the ability to collect data quicker. Now, the downside of that is we need each one of those rows to have the same amount of energy so that we could reproduce that image in the same consistent way for each of those rows. So when you go from the left side where you have a single row to the multi-row side, we have to raise the amperage in the X-ray tube, aka the MA, to a higher level to have a dose per slice equivalent to maintain that image quality. So as you can tell, when we go from 4 to 16 to 64, we have to have a higher amount of current in the X-ray tube to be able to produce that same consistency of image. So with regards to image generation, we use a function called back projection. So on the slide that you see up in the upper left corner, that's the original image, the circle with the smaller circle. And then as we're just going to produce 2 samples. So if you look coming down from the top down to the bottom, you'll see a sample that we collected across the face of the detector. Okay, this is kind of in an analog form with the orange lines. And then to the green lines, pushing data from the right to the left to that projection. So now we have 2 sample projections. And then if we push those projections back over a matrix, in the case of a matrix, it would be 512 by 512, or newer scanners 1024 by 1024, or even 2048 by 2048. We push the data back through there, and as we get different views, we push it back from different angles, and we get an accumulated image that where it says 32 there, that closely approximates what we scanned. But if you notice, it's foggy. And the reason why is the data set. As you collect more and more data, you still have rounding errors, so to speak, even though you're doing advanced math functions here. When you do projections, you still have it. So it was realized that we have to have some type of frequency response filter to clear up the image. So with that, we have what we call basically a fast Fourier transform. FFT is what it's known. It takes the data set from the view that you see over on the far left side. We then transform it with a filter. Okay, a smooth filter means small changes. We're looking for small changes. A sharp filter would be like a bone, air, bone, soft tissue transition. so we can enhance the data set by frequency. So we start off with the hump that's on the left on the bottom. We do a frequency response filter. In this case, it's showing a smooth. And then notice we have an over response edge on the front and the back leading on this element. So that's known as an artifact, a reconstruction artifact that we know about, but we also have to enhance as well to be able to leverage this filter. So examples of soft tissue would be, we want to see small changes in bone in soft tissue. So blood and brain tissue are not that far apart in CT numbers, our attenuation factors. So we want to enhance that. So that would be a smooth filter. On the case of bone and air, or bone and soft tissue, bone being a very high CT number and soft tissue being a medium CT number, aka probably around 30 or 40 CT numbers from 1,000, that's a big transition. So we'd want to enhance that. So we'd use a different frequency response filter. Luckily, what we do is take the raw data set that we scan the patient with. We save that as what we call raw data or scan data. Then we can apply this filter and create an image set with soft. Then we can take the same data set, apply a sharp filter, and then we have two DICOM images from the same DICOM, not DICOM, but raw data source. So we can take that data and manipulate it in many ways to enhance what we're trying to achieve by looking at what happens with the patient's anatomy. So now that we have that filter applied, aka in this case, it's a little bit sharper. We have our back projections being pushed back. We had two projections back, then 4, then 8, and then 16, and then 128 shows pretty much what we originally scanned. 128, no filtering, shows if we didn't have a filter applied. So all CT scans by default have a default filter applied. We may change those filters to enhance different data sets that were our structure sets that we're looking for, but we'll always have a filter applied. So now this comes into the scaling system, okay? So as I alluded to earlier, we have a standard worldwide that we could use to base scanners on, and that is distilled deionized water. That attenuation coefficient for that material is going to be the same no matter where we're at on this planet. Water is assigned to a 0 for the scaling system. Air is a -1,000. It's the least attenuating. It's what's in our lungs. And then bone approximates a +1,000. So that's a normal scaling system for Hounsfield or CT numbers. So one of the things we could do with CT scanners is obviously qualify this with phantoms. When we're calibrating the machines, we calibrate them with water. Daily air changes a little bit on every day. The barometric pressure, the humidity in water, dust in the air, all those things contribute to changing air. Also, the sensitivity of our system, whether the detector is warm or cold, could even affect some of our CT scaling. So we have to validate that we're at the same temperature and the room temperature needs to be stabilized. And then also not using tap water. So I've seen phantoms sometimes topped off because they get air bubble or something with tap water, and you see things growing in that phantom. We always try to make sure when we are servicing a CT scanner that water is a known quantity. So if we don't know what's in that phantom, we'll pour it out. We'll put distilled deionized water in it, and then verify our calibrations. Bone is emulated by a material called Teflon in most cases, so that's in the high 900 range for CTs. So one of the things that when we see a grayscale image, we're displaying the scaling factor of black to white, maybe in 64 levels of gray. But we could change which part of that data set we want to look at. It's called window and leveling. But as you can see right here, we have air down at the bottom with regards to the left-hand scaling, and then we'll see water in the center, and then calcification or bone up to the high 1000s, okay? So realize that we have to encompass the whole body with regards to it. So then between a minus and a +100, you'll see that scale expand over, where we basically can see fat, white matter, gray matter, blood, kidney, those kind of things. So depending on which material we want to enhance the view of, we will pick a low frequency filter, a soft filter for like body parts with regards to tissue in that plus to minus 100 range. But with regards to other bone that we want image, bone can, we would have to shift our scaling system up. Also, if we want to look inside lungs where there's a lot of air, we would be looking at more of a negative number, where even though there's soft tissue there, it's surrounded by a lot of air. So we'll see the scaling systems come in. We have to guarantee this scaling system works for a CT scan to be considered valid. So a lot of QA is involved with image quality analysis to validate our CT numbers are within spec, okay? So when we go back to look at an image now, remember we talked about we actually acquired it with a thickness, a slice thickness. So every spot on the image would be an average of that. So if it's a 1 millimeter scan, there'll be an average of material of 1 millimeter that we're looking at as far as a thickness. If it's 10 or 20, you'd be averaging more material, aka blending soft tissue and bone together. Not as well defined on the z-axis, but it may be what you're looking for if you're trying to acquire an image quickly. So the thinner the cut would be better because it would represent Z in a better, stronger way. So every one of these elements that was back projected, we now have this grid. We call, basically, this would be a completed image, and this one shows 512 by 512. So every one of those elements that we see on the screen is actually a voxel. Okay, it has depth to it, has X, Y, and Z axis values to it. And then what we could do is we could put a region of interest over the top of this, and then it will give us what the CT number is for that region of interest. It'll give us a means number, which is the average value, and then it'll tell us how much noise is in there. If it's just one pixel, it's not a sample of multiples. So it'd be a single, it'd have 0 standard deviation. It'd just have a means number. But if we took a group of those elements, then we have a mean, and then we would have an average. And the average is the mean. Then we'd have amount of standard deviation, aka noise in the image. So we could minimize standard deviation if we want to by different techniques. So this is the same image on the screen, but we're enhancing different details that we want to look at it with regards to window level settings. So the lungs I'm looking at on the left-hand image, trying to determine what's going on with maybe the tubes or any other detail in the left or right lung. And so my window level scaling represents the gray scales, so I can enhance the data set there. On the other hand, I may want to be looking at the aorta or something else in the same area in the chest, and I would change my window level settings in grayscale. Now, if I put a region of interest box in either one of these images, even if I couldn't see the ROI box very well, I would get the same numbers out for both means and standard deviation. Okay, so it doesn't change the root data set, it just changes the way I display it. So images that are actually filmed or the doctor views at, if they're hard copy images like film, they might even actually have shot 2 different pieces of film to represent this view. On the other hand, if a doctor is using a workstation, he could change the window leveling to enhance which one he wants to view at that given time. So this is an example of some of in the United States, we use the ACR Phantom. Physicists will come in every 2 years and validate your scanner can resolve these elements. So there's published numbers for them. Instead of using distilled ionized water, though, they use a material called plastic. That's plastic, but has the same attenuation coefficients as water. And so we can check in whether polyethylene, bone, or air. In this case, it'd be just a void in there, and acrylic. We have the ranges of CT numbers. You can tell polyethylene and acrylic gives us the high and low ranges of soft tissue of about a plus or minus 100. The Phantom will have a little bit wider aspect to that. Water will be in the center of that scaling. And then we also have to be able to determine distances. Sometimes biopsies are done with patients from CT scanners and also radiation therapy planning. So we actually have a couple of BBs that we can measure 100 millimeters to see if the scaling is actually right. And then one of the other things that's very hard to tell on a CT scanner is resolution. We want to make sure our resolution matches really well. So not only do we have line pair resolution, like on the scaling that we see here, with represented by the numbers, there'd be different line pairs, but also on what we call B, where you have different size elements there. The difference between the material is only 6 CT numbers difference in that phantom. So if I don't resolve that 6% CT number difference, I can't see small changes in CT numbers. So one of the things could be maybe the technique wasn't high enough to basically enhance the data set, or the wrong filter was used, some of those things. So we always are validating the quality of the images we generate on a CT scanner. So it's pretty exacting. Over the time, the scanners have been much more reliable. Okay, we had analog controls for X-ray and those aspects in the early days of CT. Almost everything now is computerized control and digital. So X-ray, beam, quality, those kind of things are much more consistent today. And that would affect this image quality as well. Different KVs, we have different calibration factors for different KVs. So typically we'll have 80, 100, 120, 140. Some scanners only have 3 KVs, 80, 110, 130, depending on the manufacturer. But typically we start off 80. 80 kV would be used for more pediatrics. You don't need as much energy to get through a patient that's small. And then when you have patients that are a little bit larger like me, you might actually be doing. But if you could tell, there's a lot of subsystems with regards to CT. And with regards to those subsystems, obviously we're dealing with image reconstruction. So we're dealing with the console on the far left-hand side. On the top right would be the table control, advancing the patient in and out. Then we would have stationary gantry control that controls the tilt of the gantry, axial speed of the gantry, and then basically triggering. We would get figure out when we need to trigger a data collection from the detector, and that would be sent to the rotating frame, so that we would have a selected KV and MA for the X-ray tube, aperture for the collimator, and then the detector would receive that X-ray data and then convert it based on a trigger. And then we basically would do like 984 triggers per full 360 of data. Okay. I'm going to try to move through these a little bit quicker because I'm sorry I lost you guys, but I can answer any questions. So with regards to this slide deck here, this is more of a block diagram view of that scanner with regards to the gantry rotation itself. So we have on the right-hand side, the rotating functionality, onboard rotating computer, ORP, X-ray generator control, collimator control, the DAS, and then once that DAS generates a view, the fiber optics would then send that through transmitters over to receivers on the stationary side. We would take that raw data set and then build a volumetric data cylinder that we would then prescribe images out of and reconstruct DICOM type images, okay? That would then be displayed on the operator's console so they would know the progression of the scan, okay? So obviously this is all spinning around the patient. So luckily there's covers to hide all this transactional stuff happening. The patients just hear things whizzing, right? Example of the console. In this case, the host is obviously with the operator interface to tell the scanner what to do, and then the software would then tell all the subsystems what function happens when, and then the dig would receive that data in, push it to the raw data disk at the bottom, and then the dig and the verb would recon that data into DICOM images that would then be sent to the host for display. Okay. So quite a few things are happening. That we have diagnostics for almost all these functionalities that we would have to do depending on what we're doing to troubleshoot. X-ray tubes, like we said, are only 2% efficient. So X-ray tubes become printer cartridges with regards to CT. Average lifespan is anywhere from 22 months to 26 months, you know, obviously about 2 years. That's on an average used machine. Some systems we use more tubes per year. Others, it might be a little bit spread out based on lower usage. But we're dealing with 140,000 volts in the example of here. And with only 2% efficiency, we have to make sure everything's clean. All the fans are blowing, oil unit with regards to flow, and then all the filters would be cleaned during PMs as well. So another item that's on the rotate frame would be the inverter here, driving the high voltage tank. That's a multiplier to get us that 140,000 volts. And then we would be spinning the X-ray tube anode as well, and then controlling the filament temperatures with regards to how much MA we need for image quality. And then we have our detector that is hidden behind that light seal plate here. But the crystals have to be maintained at a pretty consistent temperature. Their transfer or leakage current would change a little bit based on temperature. So we have a temperature regulated detector. And then we have the A to Ds behind it. In this case, 64 slice system. Each of those rows has 64 crystal elements as far as depth on Z as well. So we have quite a few analog to digital conversions happening. This is sampled one trigger will sample all the data from this detector, and we're doing that 936 times per gantry rotation. So a lot of data is being moved. That's why fiber optics are being used a lot to move the data from the gantry into the recon subsystem. And that's why the volume of data is very large. So common issues like we talked about with CT is X-ray tubes are my biggest cost with regards to understanding. And we're talking about in some systems, the X-ray tube is 184,000, 190,000. Some of the higher end systems, they're out there even higher. There are systems that have 2 X-ray tubes. In the case of Siemens, they have a flash and a couple of different models where you have 2 X-ray generators, 2 X-ray tubes, 2 detector sets, all that in the same gantry. So cost to serve is quite high. And then we also have the X-ray generator supporting parts with regards to inverters, high voltage tanks, and the controls for those are high usage as well because we're using a lot of current through the X-ray tube. With regards to computers, we're not only controlling the system with the computer, calling out protocols, and then using the user interface to initiate a scan, but then that raw data volumetric set that we've had is now we're pulling data out of it, depending on which frequency response filter we want to enhance bone or soft tissue. We can also cross-plane instead of just producing images from an axial perspective. We could also do it periaxial, like the length of the optic nerve, those kind of things as well. So we could take that data set. Once that data set is then used to produce a complete image set, DICOM image set, that would be overwritten. Okay, so we're using hard drives quite in a hard way with regards to that raw data drive set. Okay, so we're moving a lot of data to them quickly. They're 10 or 15,000 RPM drives, and they're on 24/7 typically. So they will wear out. In the case of newer systems, they may be using solid state drives for that functionality as well. Then we have our detector elements with regards to the crystals in those detector elements will degrade under radiation hardening. Then the converter boards behind them are more integrated, so the whole module may be replaced or aged out that we'll have to replace. This typically the center modules go first because they see more radiation than the edges do. Okay. Then we have axial drive motors and amplifiers that drive the system. Okay. And then we have patient table where the patient's advanced in. Table errors are very low in the priority list as far as normal failure modes. Okay. So we're looking from a hierarchy at the top of all the way down is with regards to the kind of the cost to serve of a machine as well from a failure perspective. Okay, X-ray tubes don't fail every day. It's the cost that we're looking at in this context. Okay, You'll see small errors and those kind of things that might be components that wear out. Okay, but from a system perspective and a cost perspective, this is kind of the view that we typically see with regards to service costs. So independent groups, we will see will obviously require support. In this case, whenever we decide we're going to look at service in a machine, we look at the cost of glassware, aka tubes. Some of them aren't glass anymore; they're metal and ceramic, but we still call them glassware. So that's about 70% of what we look at as a cost to serve. Then we have the other supporting parts, about 20%, which would be X-ray generator parts, computers, and then consumables. There's like brushes and other things that are used during PMs, like filters, that would be leveraged as well. Training is one of the biggest things that we can do to save money. Okay. The better trained you are, the less parts and time the site is going to require to be supported. So, we've heard the word shotgun before with regards to throwing many parts into a machine. Obviously, that's very expensive, but you also don't necessarily achieve a quick result, with regards to parts. One part is going to fix it, not five. So you may be wasting time putting in the other five. But knowing which of those parts to replace, it being wise in that process, and doing a first time fix, all relies on you being trained properly to do the job. Okay. And with regards to training on CT, obviously we have unique challenges with each model of CT that we have to support during that training. So not all CTs have the same failure modes. Each OEM has a different kind of service tools that they provide for you in the third-party space. So all those things come into training as well, and knowing how to leverage those tools. Theory is one of the biggest tools that we can have in leveraging theory. But over the years, third-party tubes have allowed the market to really exist in a strong way. And in case on GECTs right here, we have the DA200 tube that's been used in the early Lightspeed series to bright speeds today. And then also the Optimus 540, those products as well. Then we have the 200 means 200 millimeters. So GE may call it a MX200. We call it a DA200 because of the Dunley terminology. 240G, larger 200 millimeter, 40 millimeter target for the VCT and some of the other products that are VCT based. And then the Optimus 660 could do a faster gantry rotation, so it required stronger bearings, so that's the P40 version. And then later on, GE released the Revolution EVO, Optimus 660 Gen 2, and some newer versions based on that product as well, which uses liquid bearing version of that tube. So we actually bought some of these systems to actually validate the tube from Dunley with regards to it. So these are products that are available from AllParts to support your CT products. As far as bays, these bays are leveraged not only for training, parts repair, parts validation, tube testing as well. So quite leveraged. These are not the only bays that we have here. These are the only CT bays. We have X-ray bays, we have MR, we have ultrasound, and cath labs as well. With regards to the GEs, obviously we've got a Revolution EVO, Optimus 660, a Brightspeed, two VCTs. They have different detector units on them, one VDAS, one HDAS. So we have an example of both to test those modules and those detectors. And then we have the Lightspeed 5X16. That's a 2003 era product. So a lot of span of history on these products. On the Siemens side, we have the Emotion 16, Sensation 64, Definition 128, and the Perspective 64. The perspective and the emotion are very closely related, so we actually have a class that teaches both those machines in the same class. So we have a lot of bays, a lot of engineers here that are repair techs that can take care of these products as well, and then we're leveraging for training quite often. Phillips also leverages the same training that the customers get from AllParts. So we do have a search page that you can look for parts on the AllParts website, okay, with regards to what we offer. And training can be found on that website, on the website as well, okay. So examples of courses that we operate with regards to currently, the GECCTs, we offer exposure to a lot of different models in a 2-week course. And again, the emotion perspective is a 2-week course as well. The sensation series is a 9-day course, and the definition AS series is a 9-day course as well that we offer here. Okay. All right. So again, we support all these different modalities here. I was just fortunate enough to share the CT aspect of it with you today, and then we can move into the Q and R, our Q&A session now. And I apologize for my mic getting turned off. Not sure how that happened. So I'm open now.
Okay. Thanks so much, James. Yes, we are over our time, unfortunately, but
Yeah.
thank you so much for your time today. And I apologize to the attendees for the minor kind of technical difficulty, but we got over it, so that's good. Anyway,
Okay, I apologize for that. Yeah.
Anyway, James, thanks for a really informative presentation. Thank you. I'd like to encourage everyone to visit today's sponsor, AllParts Medical, to learn more about the services they provide to the industry. So please visit allpartsmedical.com. And as promised, the answer to today's trivia question is Garfield. So congratulations to our winner, Laura Kroger in South Dakota. So Laura, enjoy your AirPods. And just a quick reminder, you can obtain your C certificate by completing the post-webinar survey, which will be emailed 1 hour after the completion of today's webinar. You must complete the survey to receive your 1 CE credit from the ACI, and you'll be able to download the certificate directly from your computer once the survey is submitted. If you have any questions, you can reach us at webinar@mdpublishing.com. Now, if you've missed any of our past webinars, including any by AllParts, please visit webinarwednesday.live to view our whole webinar archive. We'll be back soon with another webinar and, of course, another 10th anniversary prize. So please visit Webinar Wednesday Live for more details and complimentary registration. Thank you once again for your time today, and I hope you enjoy the rest of your day.